A red cliff above red water, spinifex in the cracks, cold wind off the Gulf of Carpentaria. You have seen this coast on a map and you think you know it. You do not. 800 kilometres of red dirt along its edge and barely 4,000 people on the whole stretch. Below 20 metres, underground water of the Great Artesian Basin sits at 60 degrees Celsius in July, every July. Hundreds of stone fish traps along the coast that no survey sheet can date. A bauxite ledge 4 metres thick running for kilometres just under the surface. Those 4 are one story, and the chain closes at the end. If you have driven the track from Normanton toward Weipa, you know the feeling. You leave the bitumen behind inside 20 minutes, and then the road commits. Red corrugations, creek crossing, scrub. 4 hours later, you are still doing it. Drivers file that away as remoteness. Australia is big, the far north is empty. Look at the local government area numbers and that track stops being ordinary. The drive from Normanton to Weipa along the western side of Cape York Peninsula is roughly 800 kilometres following unsealed roads. The straight-line distance is 520 kilometres. Terrain and river systems force a massive detour onto every road, train and four-wheel drive because there is no highway through the middle of the low country. At the two ends sit the main settlements. Weipa, with around 3,800 people, built almost entirely around bauxite mining. Normanton, with just over 1,000 residents. In between, you pass places like Koanyama, Pompuro, and Arukan. Not one of them is a city. Pompuro has about 700 people. Add the First Nations communities and cattle stations, and the whole stretch comes to somewhere around 4,000 people spread across 800 kilometres of coastline. Sparse and empty are two different words, and the difference matters here. Across these local government areas, the majority of the population identifies as First Nations Australians. The traditional owners of this western coast include the Wik, Wikway, Kugu, Olkola, Yirruront, and Thayor peoples. Their connection to country spans thousands of years continuously. What that coast never got from state authorities was agricultural development, rich topsoil, easy river flats, and market towns. The permanent road came late, carved out in the mid-20th century by post-war resource exploration rather than pastoral expansion. Before that, supply came by coastal lugger or barge during the dry season. So why did it make roads so difficult to build, and why was the soil beside it considered so poor for cropping? The answer is an ancient geological basin and a weathering process that stripped the continent bare. Hundreds of millions of years ago, a massive structural depression took shape across the eastern and central parts of the continent. Geologists call it the Great Artesian Basin and the Carpentaria Basin, created as tectonic forces warped the ancient bedrock down. Over millions of years, inland seas flooded the area, laying down thick sheets of sandstone, siltstone, and mudstone. The scale of this water-bearing system is vast. It covers more than 1,700,000 square kilometres, stretching under a fifth of the continent. It holds an estimated 65,000 cubic kilometres of water. It is not an underground cavern, but an enormous sponge of porous rock trapped between layers of clay. Rain falling along the Great Dividing Range filters into sandstone and creeps westwards underground at a rate of a few metres per century. By the time that water reaches the western edge of Cape York, it has been trapped underground for hundreds of thousands of years, absorbing geothermal heat. In many bores along this coast, water emerges under its own pressure at temperatures well above 50 degrees Celsius. Then, millions of years later, intense tropical weathering took over. During the Paleogene and Neogene periods, hot, wet tropical climates baked and drenched the exposed land surface. Rainwater, saturated with carbon dioxide, dissolved soluble silica, sodium, potassium, and magnesium, flushing them out of the upper soil column. What remained near the surface were insoluble ferric iron oxides and hydrated aluminium oxides, a thick crust known as laterite. Where aluminium was concentrated, it formed bauxite. This left a band of bright red, nutrient-poor capping running for hundreds of kilometres down the coast. This deep weathering profile explains the agricultural isolation of the western Gulf Coast. The topsoil contains almost no available phosphorus, an element critical for plant root development, and holds very low levels of organic matter. When European pastoralists attempted to establish cattle grazing and cropping across the Gulf country, livestock suffered from severe mineral deficiencies unless supplemented with phosphorus licks. The climate adds another barrier. Bureau of Meteorology records show this coast receives almost all its rainfall during a few intense monsoonal months, followed by absolute dryness. During the wet season, low-lying rivers like the Gilbert, Mitchell and Flinders swell to form inland seas tens of kilometres wide, turning the coastal plain into an impassable maze of water and mud. The traditional owners had this country understood long before any surveyor set foot on it. They understood seasonal movements, deep permanent soaks fed by the underlying basin, and coastal fish traps that provided reliable food. Along estuaries and tidal zones, stone structures and wooden weirs were constructed to trap fish as the tide receded. Lines of dark ironstone rocks were laid out across shallow channels, forming complex walled enclosures that worked in harmony with the massive tidal ranges of the Gulf. Survey work by archaeologists and state institutions has recorded numerous sites, though many remain unmapped in official registers. The land itself has been slowly changing position. The Australian continent drifts northeastwards on its tectonic plate by roughly 7 centimetres a year. Combined with post-glacial adjustments of the Earth's crust, the coastline we see today is only a snapshot in time. Thousands of years ago, when sea levels were lower, the Gulf of Carpentaria was a vast freshwater lake surrounded by open plains, connecting northern Queensland directly to Papua New Guinea. As polar ice caps melted, the ocean rose, flooding the lake and submerging ancient sites beneath meters of seawater and sediment. And the same tropical weathering that stripped the topsoil left behind one of the largest concentrations of bauxite on Earth at Weipa. In July 1955, geologist Harry Evans, searching for oil and gas for the Froome Broken Hill Company, recognized that the red cliffs rising above the beach near the mouth of the Mission River were high-grade aluminium ore. Subsequent drilling confirmed the Weipa deposit was one of the largest continuous reserves of aluminium ore ever discovered. To understand how this coastline was officially mapped, you have to look at the tools that unlocked it. For decades, official understanding depended on what could be seen from the deck of a boat or drawn on a paper chart. The first major shift in perspective came from airborne geophysics. Beginning in the late 1950s, the Bureau of Mineral Resources, which later became Geoscience Australia, flew systematic aeromagnetic and gravity surveys across northern Queensland. Instruments mounted in low-flying aircraft measured minute variations in the Earth's magnetic field and gravitational pull. These aeromagnetic maps revealed that the flat plains of the Carpentaria Basin were not uniform. Beneath hundreds of meters of Cretaceous sediments, instruments picked up sharp, linear magnetic anomalies indicating deeply buried basement structures, fault lines, and igneous intrusions. To confirm what these signals represented, geologists extracted continuous drill cores from depths of up to 1,500 meters across Cape York Peninsula. Geochemical sampling and X-ray diffraction analysis of core samples confirmed that the pisolitic gravel at Weipa contained up to 55% alumina, making it one of the highest-grade deposits in the world. At the same time, the understanding of the subterranean water system was rewritten by isotope hydrology. Researchers from the CSIRO and Australian universities collected groundwater samples from deep artesian bores right across the Gulf country. By measuring ratios of stable isotopes like carbon-14 and chlorine-36, scientists calculated how long water had been underground. Isotopic signatures proved that hot water emerging at Normanton entered the sandstone aquifers over 100,000 years ago during the Pleistocene epoch. In coastal marine environments, ships equipped with multi-beam bathymetry and high-resolution seismic reflection profiling mapped the seafloor of the Gulf of Carpentaria. Seismic waves penetrated the seabed, bouncing off buried sediment layers and revealing the drowned channel of an ancient river system that flowed across the dry Gulf floor during the last glacial maximum. More recently, airborne laser scanning, or lidar, altered how archaeologists and geomorphologists look at dense tropical scrub along the coast. Mounted on aircraft, lidar sensors fire hundreds of thousands of laser pulses per second toward the ground. By filtering out returns from dense vegetation, software generates digital elevation models of the bare earth underneath, uncovering low ridges, ancient beach berms, and structural alignments invisible from the ground. This sequence of technologies fundamentally changed the official record. Ground classified on old cadastral maps as empty or unproductive was revealed to be a complex, multi-layered system shaped by deep time and human adaptation. The fact that the western coast of Cape York is built on a massive laterite crust over a deep Artesian basin locks the region into a specific set of modern consequences. The most visible is the mining operation at Weipa. Rio Tinto operates one of the largest bauxite complexes on the planet along this coast, exporting roughly 34 million tons of bauxite in 2022. Because ore sits as a flat layer just beneath the surface, vegetation is cleared, thin topsoil is stripped, and front-end loaders scoop up the 2 to 4 metre thick bauxite layer before shipping it to alumina refineries in Gladstone or overseas. The footprint of the mine continually moves. As shallow layers are exhausted, the mining front advances, clearing and rehabilitating thousands of hectares of coastal scrub. Rio Tinto is legally required to restore mined land, replacing topsoil and replanting native species. However, ecologists note that soil hydrology has been permanently altered. Breaking up a consolidated laterite crust changes subsurface drainage. The long-term success of re-establishing complex native ecosystems remains under ongoing monitoring by state environmental agencies. Away from the mine, underlying geology forces high costs onto public infrastructure. Maintaining the 800-kilometre road network connecting remote communities is a constant battle against basin hydrology. The road base is built from local lateritic gravel, highly susceptible to washouts during the wet season. The Queensland Department of Transport and Main Roads spends tens of millions of dollars annually keeping these remote routes open, with individual creek crossing upgrades costing upwards of $5 million. Communities like Pormpuraaw and Kovanyama are routinely cut off by road for months, relying on expensive air freight or coastal barges. Then there is the water. Pastoral stations and remote towns rely almost entirely on the Great Artesian Basin during the dry season. Hundreds of bores provide water for cattle and domestic use, but because water emerges at high temperatures and contains dissolved minerals, it requires cooling and treatment. Furthermore, basin pressure has been dropping due to extensive extraction across eastern and central Australia. The federal government, in partnership with the states, has spent hundreds of millions of dollars on the Great Artesian Basin Sustainability Initiative, capping old, free-flowing bores and piping water to conserve pressure. For traditional owners, the consequences of this geology tie directly to cultural heritage protection. The expanding footprint of bauxite mining and infrastructure intersects with ancient sites like coastal fish traps, middens, and scarred trees. Following landmark native title determinations, mining companies operate under Indigenous land use agreements, involving traditional owners in cultural heritage surveys ahead of clearing operations to ensure significant sites are identified and protected, and financial royalties flow back into communities. Every modern intervention on this coast is an argument with the deep time processes that formed it. So, what is the western coast of Cape York Peninsula actually hiding? One chain of planetary events. Over 180 million years ago, a structural depression formed across northern Australia, catching millions of years of marine sediment. As those ancient seas retreated, severe tropical weathering stripped silica from surface rocks, forming a 4-metre-thick laterite and bauxite crust that rendered topsoil virtually barren. Beneath that crust, trapped in porous sandstone, 65,000 cubic kilometres of thermal water entered the Great Artesian Basin during the Pleistocene epoch, flowing slowly westwards. When the last ice age ended, the rising ocean flooded the ancient Carpentaria Valley, drowning river channels and leaving coastal communities to adapt to shifting tidal inlets with stone fish traps along the shore. One underlying geological process produced the hot water, infertile soil, impassable wet season floods, and multi-billion-dollar bauxite reserves at Weipa. What kept all of this off the official map for so long was not a conspiracy, but a rigid colonial definition of productive land that measured countries solely by its suitability for European agriculture. Because the laterite crust would not yield to a plough, official charts treated the coast as a blank expanse, ignoring both deep industrial potential beneath the surface and the continuous, sophisticated management of the land by First Nations Australians. Many questions remain unresolved. Hydrogeologists at CSIRO and state agencies are still working to map exact recharge rates of deep aquifers beneath the Carpentaria Basin to determine how long thermal pressure will last under modern extraction rates. Archaeologists and traditional owners continue to document marine and coastal heritage sites before rising sea levels and coastal erosion alter the tide lines once again. The modern topographical map looks neat, surveyed, and complete, but the ground beneath it remains active, shifting, and deeply layered. Which place in your own state or territory has always struck you as a geographic or geological anomaly? Tell me in the comments below, and if you want to follow more investigations into the hidden structures of this continent, consider subscribing to the channel.